be recording the session as well.
Yes.
So, for your kind information. Yes, ma'am.
Oh, now maybe you can see me for a while. Oh no, it doesn't work anyway.
No, ma'am.
Ma'am, you can switch to the application.
Yes, wait a minute, please.
No problem.
Okay.
Okay. And we'll start in one or 2 minutes. We'll introduce you, and then we'll.
Okay, thank you.
Yeah.
So, Rishabh, I'm starting the event. I hope things are ready at your end.
Yes, ma'am.
Okay, thank you. So, greetings to all our participants. I welcome you to another episode of IEEE Virtual Talk Series 2020. And today we have with us Dr. Olena Veniga. So she's from Ukraine. So I formally present a red carpet welcome to our speaker and all to our participants from within India and abroad. So I welcome you all. And to briefly introduce our speaker, so Dr. Olena is a PhD and in a Doctor of Sciences at the Institute of Mathematics of NAS of Ukraine. And she's also working currently as a senior researcher in the same institute. And currently she's working in the field of group of analysis of differential equations. She's a member of American Mathematical Society and European Women in Mathematics. She has received a number of national awards. These are in particular like Prize of the President of Ukraine for Young Scientists in 2010, Visiting Scholar Grant from Niels Henrik Abel Abroad in 2014, Prize of Presidium of National Academy of Ukraine for Young Scientists in 2014, Award for Women in Science from L'Oreal Foundation 2018, and International Rising Talents Award in 2020. So with this brief introduction, I welcome you, ma'am, for your talk. Yes, over to you, ma'am.
Yeah, thank you very much. I first of all would like to thank the organizers who invited me to present this talk today, so thank you. And I will speak today about symmetry methods in the study of nonlinear models of real-world processes. So let's start. In a wide range of sciences and application areas, from the fate of the world climate, which is a real problem now, as you know, to the state of local rush hour traffic, mathematical models increasingly provide us with valuable and practical perspectives on complex phenomena. And one of the most powerful tools to study such phenomena is to model them using partial differential equations, or PDEs. Roughly speaking, partial differential equations and models described by them are sets of equations describing the evolution of physical quantity not only with time, but also according to space variables. So actually, in partial differential equations, we have several independent coordinates, we have some unknown functions, and partial derivatives of these functions with respect to independent variables. So let me present several very well-known examples. At first I will speak about linear models. For example, linear Schrodinger equation is a central equation in quantum mechanics, and its father of this equation, Schrodinger, then received Nobel Prize for creation of such model. And as you can see here in this equation, here we really have a function psi, which depends on time variable and space variables, and we have derivatives with respect to t. And in this second term, we have derivatives with respect to space variables. But this equation is linear. The second example, probably everybody saw this picture and got set these equations, and then there was light. So these are actually Maxwell equations, which provide a mathematical model for electric, optical, radio technologies, to power generation, electric motors, wireless communications, and lenses, radars, etc. And these equations describe how electric and magnetic fields, electric field E and magnetic field B, are generated by charges, currents, and changes of the field. So this prominent model is also linear one, but you know how everything in life, everything is not that easy. And majority of PDE models of real-world processes are actually nonlinear ones. But anyway, you know, they are really used in many applications and provide irreplaceable information for use in fields as diverse as nuclear physics, wildlife biology, space and nanotechnology, building construction and investment finance, and many others. Actually, majority of physics laws are also described by some partial differential equations. And you know, if I would write a book about nonlinear partial differential equations, I would start from the rephrasing quotation from Anna Karenina by Leo Tolstoy, who started his book with the phrase that all happy families are alike, but every unhappy family is unhappy in its own way. So, you know, I would write that all linear equations are alike, and every nonlinear equation is nonlinear in its own way. And that is why, actually, for nonlinear PDEs, there is no general theory for integration. And that means that there is no also theory that could consistently provide solution formulas for such equations. So with linear equations, everything is much easier, more well-developed, and with nonlinear ones, everything is more complicated. So, but let's have some inspirational minute. You know, Marie Curie, who is probably most known female researchers from all times, she said that life is not easy for any of us. But what of that? We must have perseverance and above all confidence in ourselves. So we must believe that we are gifted for something and that this thing must be attained. And having this in mind, I would like to continue about Lie symmetries. Norwegian mathematician Sophus Lie was really gifted and probably confident in himself, so he made a try to create general theory for integration of differential equations. Because that time in 19th century, it already existed Galois theory developed for algebraic equations. So he just decided to make such an analog for differential equations. And though this didn't actually lead to the general theory of integration, but this resulted in creation of continuous groups of transformations, and now we call them also groups of symmetries, which changed not only the theory of differential equations, but also it changed geometry. You can just search Wikipedia Erlangen program, where Felix Klein used these continuous groups for describing different geometries, and later continuously groups changed the face of physics and started to, in 20th century, they started to be used in particle physics. Also, there is an article in Wikipedia, you can take a look, particle physics and representation theory. So let's 1 minute talk just about symmetry. No, from ancient times, symmetry was considered as some measure of beauty in architecture, design, and even as an important element of interpersonal attractiveness. And, most probably well known in the world example of such gorgeous and beautiful architecture is situated in India. It is Taj Mahal. And also we know, everybody knows bilateral symmetry of in biology, or like this butterfly on the screen. And also we are also, like humans, we are more or less symmetrical creatures. So, and many biologists say that the most symmetrical is in some organism. It means that it is more healthy and so on. So, but of course, probably everybody knows that now in architecture, asymmetry, like which broke symmetry actually, it is also very often used because it can make things more interesting, some, unexpected, you can see something unexpectedly asymmetrical, yes? Here, by the way, you see the pictures of actress Natalie Portman, and on the right, it is actually her photo, and on the left, it's just photo made by computer. It's absolutely symmetrical surface, so it is just mirror symmetry. And so you decide which is more attractive, absolutely symmetrical or a bit asymmetrical. But anyway, symmetry creates balance, and balance in design and architecture, it creates harmony, order, and aesthetically pleasing results. So usually we like to see something symmetrical. But what is not very expectable for some people probably, that symmetry can be considered also as a measure of beauty for partial differential equations. Not only for partial differential equations, also for ordinary differential equations. So a symmetry of a, but you cannot see it like on those pictures I just showed you. This symmetry is not graphical, and such symmetry is just some transformation, some change of variables that maps each solution of this system to a solution of the same system. Well, we usually say then that manifold of solution of some PDE system is invariant with respect to this symmetry transformation. So transformation, it's some symmetry transformations. It's such transformations that transform PDE to itself. So it is like, such something that leave it unchanged. So let's have some math now. What is actually a Lie group of transformation? Let's just imagine that we have just several variables, so t, x, and u, and we have a change of variables 1. So you see there is some functions phi, psi, and theta, and they depend on our old variables t, x, u, and some parameter a. And let tau a denote the transformation 1 of some point txu into a point tilde t, tilde x, and tilde u. So the set G of these transformations forms a local one-parameter group if the following conditions 1, 2, 3 holds. Now, I will explain you just on very simple example. After which, after this example, I can remember what is Lie groups on forever. It's groups of steps on the floor. Just imagine the flat floor, and if you just stay on the place, it is identity transformation. It is condition 1. So you stay, nothing changes. This is identity. Then you can make one step and then second step, but you can make one big step and replace your two small steps by one, and this will be composition of transformations. And also you can make one step forward and then step back of the same length, and you will appear on the same place, and this step back will be called inverse transformation. So you see, everything is easy in spite of formulas on the screen. So this is Lie group. And now what we need? We need Taylor, but not Taylor Swift, of course. We need Taylor series to connect Lie groups with Lie algebras, actually. So how we do this? If we represent the functions phi, psi, and theta appearing in our transformation via the Taylor series expansions with respect to parameter a in the neighborhood a equal to 0, we can write the infinitesimal transformation like on these formulas. You see, it is transformation which is very close to identity transformation. So t equal t tilde t equals t plus some additional terms, the same with x and the same with u. And these functions tau, psi, and eta in these formulas, they are connected with phi, psi, and theta like first derivatives of them at the point a equals 0. So these formulas gives one-to-one corresponding between Lie groups and Lie algebras. And then tau, psi, and eta, they make coefficients of some first-order linear differential operator. And exactly this operator is called Lie symmetry. Lie symmetry operator. So, okay. And so this is just an example. So an invention of Sophus Lie was to study differential equations which stay invariant with respect to groups of transformations. Let us consider just group of all rotations about the origin of the plane xy given by these transformations. You see, so it is just rotation. The corresponding Lie symmetry generator, which is calculated like you see, you should take derivative with respect to a, then put a equals to 0, and you will get these coefficients of Lie symmetry generator x. What actually stays invariant with respect to rotations? Of course, these are circles. So each circle with center at the origin, x squared plus y squared equal to some constant, is invariant with respect to this group of rotations. And the corresponding ordinary differential equations, whose solution will be these circles, actually, have such a form: y prime plus x equals to 0. So it's just a simple example of Lie group and the respective differential equations which possess such symmetry. Then, okay, how we can also use Lie symmetry for generation of solutions of some differential equations? If we will consider such linear heat equation, ut equal to uxx, it admits Lie symmetry operator of such a form, and actually this Lie symmetry operator corresponds to one parameter Galilean group, t equals to t, x equals, okay. Anyway, it doesn't matter, but these transformations, they create Galilean group. So then, using these formulas, we can create a formula for generation of solutions which has such a form. And then we can just guess a couple of very simple solutions of linear heat equation, like, for example, constant one, u tilde u equals 1, or tilde u equals x. When we substitute such simple solutions to this formula for generation of solution, we will get much more interesting solutions. We see which now depends on both x and t, and which can show which processes are described by this linear heat equation, actually. So it's one of advantages of Lie symmetries, but main advantages of these methods that if we will try to find the transformations in their general form, phi, psi, and theta, which leaves a PDE invariant, we will need to solve nonlinear and often complicated system of partial differential equations. But the problem of finding the coefficients of the infinitesimal generator, tau, psi, and eta, is reduced to solving linear over determinate system of PDEs. So we simplified our problem. We had nonlinear equation. We cannot solve it, maybe. And then if we will start to look for its Lie symmetries, we will need to solve linear system of equations, and in most cases we successfully will find them. So this approach is really algorithmic and was implemented in various computer algebra systems, like Maple, Mathematica, and so on. So if you need to solve some equation, you can use these packages, and actually they use symmetries to show you, to find solution for you. So if another advantage is that if the symmetries of differential equation are known, one can adopt standard methods to derive exact solutions. And actually, Lie reduction method is the only algorithmic technique which is applicable to any nonlinear PDE. So actually, Lie succeeded to find something which can be applied to look for solutions of any nonlinear PDE. Though some of PDEs, they do not have symmetries, of course, in this case, this method will not work. But let's think, there are plenty of PDEs. We can consider a great amount of PDEs. I mean, mathematicians consider many PDEs, but not all of them describe real world processes, yes? Only some of them describe some natural phenomenon. So, and it appears that the presence of non-trivial symmetry, it's one of such distinctive features which differ equations describing natural phenomenon or real world processes, in other words, from other possible differential equations. And here on the picture you can see Paul Dirac and Albert Einstein, and I trust them. I hope you too trust them. So Paul Dirac one time said, when he was in Moscow, he just wrote on the blackboard, a physical law must possess mathematical beauty. And when physicists hear his second statement, many of them just embarrassed, because he said it is more important for our equations to be beautiful than to have them fit experiment. But actually, Dirac was physicist, of course, and he respected experiments. But he just wanted to tell that it is very important to have theories which are mathematically beautiful, and if they do not fit experiment, maybe there is some problem with experiment. So he really believed that mathematical beauty and symmetries is some feature which should be used to single out really important models describing physical phenomena. And Albert Einstein also one time said that every attempt to establish a unified field theory must start, in my opinion, from a group of transformations which is no less general than the continuous transformations of the four coordinates. So he also believed that we should start our search from groups of transformations. Okay, so finally, all the basic equations of mathematical physics, really, they are very symmetrical, have non-trivial symmetry properties. And it means that manifolds of their solutions are invariant with respect to multi-parameter group of continuous transformations, which is called Lie groups of transformations. And there is some large number of parameters. So the requirement of invariance of an equation under some group even enables us to select equations which model real-world processes from a wide set of possible candidates. And I really love this example, especially I love to say it at some physical conferences, that there is only one system of first-order partial differential equations for two real vectors E and H, and this is a system of Maxwell equations, which invariant with respect to Poincare group. Poincare symmetry is a full symmetry of special relativity, actually, and it includes translations, displacements in time and space, rotations in space, because, our world, it is homogeneous, so we can have translations in it, and also can have rotations and also boosts or Lorentz transformations connecting two uniformly moving bodies. So why I like to say it on physical conferences, that mathematicians, without any deep knowledge of physics, just having in mind Poincare group, can get Maxwell equations. So this is really inspiring for mathematicians, of course. Okay, so to single out equations having high symmetry properties from a given class of PDEs, it's a really important problem. It is called actually the group classification problem, and this is a problem for which I work for many years already. I solve such problems. Just some example from my work. Let us consider the classical Fischer equation. You see, it is a nonlinear one because it is ut equals to uxx, okay, linear part, then plus u, actually multiplied by some constant, okay, it doesn't matter actually, and then minus u squared. So if we have u squared, it's already non-linear equation. And first, it appeared 77 years ago in papers Annals of Eugenics. So Fischer originally derived to model the propagation of a gene in a population. So it is an equation which is used in population genetics. More precisely, the dependent variable u stands for the frequency of the mutant gene in a population distributed in some linear habitat like a shoreline or something like that with uniform density. And what is surprisingly that, it's very often really when the same equation appear in very different applications. So the same equations, it is also used in macroeconomics. And it describes knowledge diffusion and knowledge distribution. I think it's quite inspiring that if we will solve this equation, we will know more about distribution of knowledge, spreading the knowledge. So then several years, many years later, just maybe 10 years ago, it was proposed to consider not just Fischer equations with A and B being a constant, but to consider such equations where A and B are functions which depends on time variable. So in practice, these coefficients, they can represent long-term changes in climate or short-term seasonality, because really time can matter. So there is sense to consider such variable coefficient models. And just using this example, I will show how to solve this group classification problem, how to find functions for which these equations will be symmetrical and beautiful. So to do that, we should first simplify our problem. And we should derive some transformations which preserve the differential structure of our class and transform only its arbitrary element. Okay, in simple words, these are also just transformations, changes of variables, which, if we will apply such transformations to one equation with some specific coefficients A1 and B1, it will go to the another equation with another coefficients A2 and B2, but it still will fit in the class of Fischer equation. It will have the same form. So these transformations are called equivalence ones, and they form also a group. You see, some math begins. So I look solving some nonlinear system of nonlinear partial differential equations. I find these transformations, how they look. This is a very actually simple example. They look not bad. There are just some functions omega and theta which have such forms. So any of these transformations will transform equation from the class just to some another equation from the class. And how we can use this? First of all, we can use these transformations to find for which B and A our equation will go to the classical Fischer equation. Why we actually need this? Because for classical Fischer equations, okay, it exists for 77 years, so many researchers studied it, and many solutions are known for it, and so on. And if we will want to find solutions for some variable coefficient Fischer equation, we just can use those results if those equations are connected. So we find such conditions which, if A and B satisfy, then it's connected with classical Fischer equations. Okay, and we also use these transformations. Okay, here it's very simple, specific equivalence transformations. You see, X and U just do not change, and T changes. And if we will make it, we will apply it to our class, A just will disappear. So, you see, we made our problem easier. We just killed one of coefficients, and now everything will be easier. Okay, so now we look for operator Q for Lie symmetries. Okay, I will not go too deep. We just use Lie so-called infinitesimal criterion, and then get some equations which connects coefficients of infinitesimal operator and also our coefficient B. When we solve all this simultaneously, we get form of Lie symmetry, operator Q, and also have some equation on B. Okay, when we finally solve all this, we get the result of the group classification problem. So what this table shows? It shows all variants of coefficient B for which Fischer equations we will have some symmetries. Then these symmetries can be used for finding exact solutions. So these cases 1, 2, 3, and 4 actually show us beautiful equations in the class. And this is the answer actually on our group classification problem. The problem of group classification is assumed to be completely solved if the list of equations which we got contains all possible cases, so we didn't miss anything. Also, the obtained algebras are maximal invariance algebras of the respective equations. That means that we didn't miss any operators. So actually, we should find everything and do not miss anything, and only then we have complete answers to group classification problem. And sometimes our classes are not that simple like class of Fischer equations. For example, in such class of equations, there are around 7 or something coefficients, and all these F, G, H, P, Q, K, they depend on T. It was, okay, equation would be too big if I put T near all of them. So, and, but we again can use our methods to simplify the problem and to get the complete result of classification. You see, so sometimes problems are simple, sometimes problems are not very simple, but the main thing that we can manage with them. So, to solve actually more group classification problems, different tools and notions were proposed for the last years, and many of them were proposed in the Ukrainian by the Ukrainian team. Professor Popovich was my supervisor of my PhD thesis, and now he works in Vienna, Austria. So he proposed many different tools and notions to simplify problems, to solve the problems. And also in my works also we proposed some tools. I think just I will not mention precisely because probably the audience in general, and it would be interesting only for specialists. But okay, we created some methods, some new notions, and some new techniques how to tackle our problems of group classifications. And actually, so our research group developed such methods. Also, we solved many group classification problems for different classes. But you know, there are still many of them to solve. So you may join if somebody wants. You know, actually, symmetries are such popular topic that I do not know any country. Any continent, probably except Antarctica, where people do not study symmetries. In America, in Canada, in India, of course, in Pakistan, in everywhere. So in Europe, there are some groups who deal with these topics. So you can join to some of this group if you will want. Okay, so actually this is what I do as a researcher, and for what I got many prizes. And thank you very much for your attention.
Yes, thank you so much, ma'am, for a very informative session. So I congratulate you for the very informative talk. So now declare the session open. So if participants have any questions, so they can post in the chat box, or you can directly interact with ma'am by unmuting yourselves. Yes. Any questions from the participants?
I can take one. I have one. Am I audible, Anupama?
Yes.
Yes, I think Mohammed is saying something.
Okay. He can say first, then I can take.
Yes, Mr. Mohammed, over to you. You can ask your question. Yeah. Yes, please. Rishabh, I think you can take over.
Okay. Okay. Thank you. Mohammed, you can take your questions after me if you want. First of all, thank you for the session. I actually would like to know that since you are working in this area, we usually hear about the, right now during the COVID session also, we are hearing that drugs and drug simulation and chemistry simulations are taking place using the softwares. They are involving some kinds of mathematical equations as well. So there are simulation theories we are already aware of, but how can you be, we can link these, first is the probability density function, like for an example we can take, density function we can take. So how can we make sure that density functions and these are the compatible? Is there any way of finding out to linking the mathematical equation with them, or what are the parameters sort of? Can you comment on it?
Actually, I'm not sure that I got your question properly. You say that there are some models which describe this, you mean something applicable to medicine and so on, yes?
Yeah.
Okay, so actually, when we already got the solution, we have exact results. We can, how to say, we can make a graph, yes, and we can then just compare it with the data which we have, and also to so we can compare our results and the real data. We have some problem. So, because
there are theories which indicates that it can be, predefined, before actually doing the experiments and with the help of simulations.
Again, I hope I got your question correctly. Some people from our department worked with some experimentators, so they got just data tables, and actually using Symmetry also created a model which will describe this process. So I mean, it is possible. I just didn't work with that, but it is possible to really apply it to some specific problem very real.
Then okay, if it's possible, then how much data set we are talking about? It must be very high, large number, or be very small number. So what can be the size of the data set so to make it possible?
Sorry, to make possible what?
You are saying that it might be possible these processes, the predetermination or prediction of these structures without any actual experimentations. So there must be, we kind of need some computing power, or number of data sets to evaluate or to get to these data. So what can be the number of it? So
I just actually, I always worked on these problems just like fundamental research. So I never worked with such data or something, because I usually created mostly methods, then worked with such applied things. So I just do not know. I should probably ask somebody at the department work.
No problem, ma'am. No problem. So yeah, I have expected that it's kind of maybe off the topic question. So it's no problem. Okay. We can take the next question in the chat box. Yeah, from the strategies.
Can I ask one question?
Okay, Mohammed, you can go ahead, please.
Okay, what I'm interested in the solution of the partial differential equation. Whether the how we can check the existence and the uniqueness of the solution for the Fischer's equation. Do you have any theorem or something developed to check whether the solution exists or not? If it exists, whether the solution is unique or not?
Okay, I got the question. So, about Fischer equations, all that was done many years ago, because Fischer equation is a particular case of Kolmogorov-Petrovsky-Piskunov equation, and as early as in 1937, all theorems were proved by Kolmogorov itself. So there are papers about this in some Moscow bulletin of some university. So yes, we have these theorems. And about Lie method, we actually always get solution. So we see it. I mean that it exists for sure. But usually we do not check this uniqueness and existence. There are people who works, in differential equations who work on that. So we do other things. We actually get the solutions and show the solutions, not just prove that they exist. Okay, but thank you for the question.
Okay, what really confuses me is I don't know how you solve the PD, the Fischer equation. So in my case, we have got several numerical approaches to solve this Fischer equation. I mean, different numerical approaches. So my question is that how we can check and compare the solutions, because ultimately we are interested to find out our solutions more accurate in terms of consistency and the convergence criteria, and from the past research, we already know some solutions of Fischer equations. And if we can change the equation a little bit to some modified other forms, and we want to solve that partial differential equation, so how are we going to compare it with the other solutions that are always available in the literature?
Well, I hope I understood what you mean. Actually, when we have exact solutions, one of purpose to find them is because they can be used then to be compared with numerical solutions. And I mean, people who works in numerics, they need real exact solutions, yes, to check the accuracy, yes, of received solutions. So I mean, our solution, we do not compare them with numerical solutions, but people who work in numerics, they can use our solutions to check their results. If I hope I got your question.
So for the nonlinear case, like you have mentioned in the Fischer equation, the U term was the which makes the Fischer equation to be nonlinear. How are you going to solve nonlinear equation analytically? Because I know that nonlinear you can only solve some numerics approach to the partial differential equation.
So probably I needed to give more details about Lie symmetry methods. What is the main feature of it? It is the method which is called Lie reduction. Why it is the reduction? So if you have a symmetry operator, so you have this one parameter Lie group of transformation, you can make such a substitution, so you can change variables in your equation in such a way that one independent variable will disappear. So if I have my symmetries, I can reduce my 1 plus 1 PD to an ordinary differential equation. And this ordinary differential
system of ordinary differential equation.
Not system, just one ordinary differential equation. But then often it can be solved, and then you just go back because you have the formula which connects your 1 plus 1 PD and an OD. Then you get solution of an OD and go back. And also sometimes we also use this approach for solving boundary value problems. So if we have some problems for PD and have also initial and boundary conditions, we can also reduce our problem to the problem for ordinary differential equation with some boundary conditions. And sometimes we even use numerical methods then. That I mean, again, we have connection, we have well-developed methods to study this boundary value problem for OD, like finite difference methods or something like that, and then we go back to get solutions. So actually, this approach can also be used in numerical topic.
Yes, thank you. I have more questions, but I think I should stop here. So I'll give the floor to other people, okay? Thank you very much.
Okay, thank you.
Yes, thank you. Any other questions from the participants?
Actually, I got one more. Ma'am, you said there is a need for the exact solution for solving the PD equations. Yes. So, ma'am, what if we don't have exact solution? How to approach for the solution to that problem? Because actually, I work in the system of microscopic particles. So, there in that scenario, it's impossible. It's kind of impossible to have the exact numerics of the situation. I think. Familiar with the Heisenberg principle of uncertainty is there always. So if we don't have the exact value, how do we approach to the solution of that problem?
Okay, I just do not know which equations you had in your theory, yes? So where those PDs or what?
If we consider, in general,
Okay, I just want to get the point, how do you know that it is absolutely impossible to get exact solutions for your? Maybe you just do not know how to find it, or I mean, whether all existing methods were applied.
We can take an example of an atom. So
okay.
So according to well-defined law, we can surely say that there is impossible to measure the momentum and the position of electron in an orbit at the same time, exact position of the electron. So how do we, if we want to solve using the visual science and the computing, how do we approach this problem?
Okay, let me answer in such a way. If we have some partial differential equation model, we look for its symmetries. If they exist, we can try our method. If they do not exist, then this method will not work. So it depends on the model. So you should just check whether these symmetries exist to apply this Lie symmetry method. If they do not exist, then this method will not work, and then I will not be able to find anything. So I mean, it is absolutely. I mean, it is okay. Of course, you can have such models that this method will not work, but at least you should first check.
Excuse me, I can make this question clear to the person who is asking. I don't know. See, the motion of electron is not classical. It's a probabilistic. You cannot find the exact location of the electron in space and time. So what Heisenberg uncertainty principle says, you can find the most probable region of finding an electron at a certain time. So you cannot locate it. This is what the difference between classical mechanics and quantum mechanics, that the motion of the electron is probabilistic. You cannot find the exact position in space and time, but you find the most probable region delta x, where there is more chances of electron at a certain time. So the motion of electron is always probabilistic. It's not just like classical motion, like we walk in the street or the cars on the road. So you cannot find the exact position of the electron.
We can by this we can have the well-defined area or the region to look for.
Yes, exactly. So delta x in the Heisenberg uncertainty principle is the most probable region for the electron, because electron is not classical motion. They behaves in the quantum mechanics wave.
Okay.
Yes.
Yeah. Actually, for the question I have taken as a sample question, okay. So we can have that area, triangulation.
Exactly. For example, if you're finding an electron at certain point in space and time, so if you solve the equation for it, so you get the most probable region that in this time electron will be most probably from here to here. You cannot find exactly the point where the electron could be. This is how because electron speed is 99.99% of the speed of light. So that's how it's very difficult to locate at a specific point.
Thank you.
Thank you.
I could add that in fact we can find exact solution of Schrodinger equation, but this exact solution will give only some probability for characteristics of electron. So
I'm sorry, but we are not able to. I'm not able to hear you.
Yes.
Yes.
So thank you. Let's move to the next question. So we have two questions, ma'am, in the chat box. So first question is from Zen. So he's asking, is it possible that we can use the Lie symmetry for fractional order PDEs?
Yes, it's for sure. But just one ask: don't say that it is Lie symmetries. It is Lie symmetries. We have no lie in our theory. Okay, I'm just joking that, it is controversial titles that some people think that it is lie theory, not Lie theory. Okay, so yes, it is possible to apply these methods to fractional order. You can just search Google Scholar. There are plenty of papers on application of Lie symmetries to fractional order differential equations. Also, even for some stochastic differential equations. Just for some stochastic equations. So, okay.
Okay, thank you. So next question is from Satyajit. So he's asking that, can we use nonlinear model for prediction?
Of course, for prediction of what? But of course we can. I mean that I talked from the very beginning that if we have a nonlinear model for describing some real world phenomena, we can use then solutions to predict the behavior of this process.
Okay. So I hope the answer is clear to Satyajit. If not, then you can directly interact with ma'am.
Okay.
Yes,
Okay.
any other question from the participants?
Okay, ma'am. So can you please, tell about the problems students can take in this area, research scholars can take in this area, few topics.
You mean which problems they could take for the beginning, or which people they could connect? Please. Problems.
With you for the problems.
Okay. First of all, I would like to say that to be introduced in this topic, there are some books. For example, book by Peter Hayden about this. He works in UK, and also book by Peter Oller, who works in the US, and some other, of course, but probably Peter Hayden's book is very easy to start. Okay, and actually how we look for problems, okay, I just read regularly some papers. I mean, this some partial differential models. So, and if I think that it is interesting to study, so I do that. I mean that probably in science, to find some problems, you should just read a lot of literature always. And also, sometimes problems come from the reviewing of papers, because group classification problems, they are not so easy sometimes, and if not to apply modern techniques, often authors miss some cases, and then it's not classification, it's not complete. So if I see such a paper published, I often make a comment on such paper, because I want to have complete to somewhere in literature there should be complete result. So okay, hopefully I answered your question.
Yes, ma'am. Yes, ma'am. Thank you, ma'am.
Yeah, thank you.
Ma'am, we have one last question in the chat box that we can take for today's session. So the question is from Shantanu. So he's asking that, ma'am, during your research time, how has the application of PDES evolved over time?
Application of PDES?
Yeah.
I'm not sure that I got the question. That how they changes over time. You know, I'm probably not so old. So for those years I work in this, they are not changed so much. I just.
Rishabh, could you take? I think maybe my audio is not clear. Rishabh, last question, could you take?
Your audio was clear, ma'am. Got your question, I think. Hello, ma'am.
What?
You got the question, Anitma's?
In chat?
Yeah. So,
okay. Yes. I got the question, but I really. So how application of PDF has evolved over time? During my research time, I actually I don't know. I think they evolved. Okay. Anyway, you cannot get what is it. Okay, my answer is the same. That during my research time, there are no such big changes in this.
Okay, so with this, I think we can conclude today's session, and let's thank the speaker. Thank you so much, ma'am.
And thank you.
Session. Participants really enjoyed because we can see many appreciation comments in the chat box. So with this, we present a token of appreciation and recognition to ma'am as being our keynote speaker for today's session. So Rishabh, can we have the certificate on the screen as a virtual memento for our speaker? Yes, ma'am. This is a virtual memento from our student branch.
Yeah, thank you for the invitation. It was my pleasure to speak here. So, thank you.
Thank you so much, ma'am.
Bye.
For your time and for sharing your knowledge with all of us. So now I request all the participants if they can turn on their video so we can have a group picture with our speaker.
Thank you, ma'am.
Session. Yes. Our participants can turn on their video. We can have a group picture. And I really thank all our participants for joining today's session. Yes, I invite all our participants.
You know, I should apologize that somehow my camera cannot be connected. It's very pity for me.
No issues, ma'am. We'll add your photo, ma'am. Yes, so thank you. I've taken through screen.